This is my solution to Paul McWhorter's Rumble in the Jungle Grand Challenge. Create a program that does a binary up-down counter using push buttons entirely within the Raspberry Pi Pico PIO block. Quick overview. This solution uses two state machines. One state machine manages the count up portion, and the other one implements the count down part. There is a shared counter between them, which will have to be synchronized as they are each attempting to update it. Some references on how synchronization is done are in the RP 2040 datasheet. Here's the state machine 0 decorator and code. One change from previous decorators is we're changing the in shift direction from left to right. The code begins with 3 initialization instructions. The first 2 turn off the LEDs, and the third one, IRQ4, sets the IRQ flag bit. And what's that about? Is from the data sheet, there are 8 flag bits. The lower 4 can be masked into an interrupt request line, which we don't want. So we're not going to use the lower 4, namely 0, 1, 2, and 3. We'll use one of the upper 4. These flag bits have 2 main uses. We're going to use that second one, synchronizing between 2 state machines. So this IRQ4 instruction is setting the flag bit for IRQ4. And we will think of it as a latch that protects a shared resource. Remember, that's going to be our counter, and in our case, we are going to use the 4 LEDs, well, actually the GPIO pins, as the counter. So when the latch is set, has value 1, that means the latch is free. It's available for use. So we can, or the resource is free. When the latch is clear, value 0, the resource is in use, you can't have it. So we start off with the latch being available. Now we enter our standard code. Remember, this one is doing the count up, so we're waiting on pin 14. So this waits on pin 14. Debounces the press, waits for it to be released, debounces. Now we enter the code where we add, and notice this warning message. Both state machines have similar code, so they're going to both be trying to do this code. We have to protect against that. And here's how we do that. We issue a wait instruction. Now, if you recall, IRQ flag 4 was set to 1 originally. This line is waiting for that to be 1. Wait on IRQ flag 4 to be 1. The minute that happens, the instruction sets that flag bit to 0, and that ends the instruction. So what that does is it latches the resource, protecting it from being used by the other state machine. Because when it issues its wait, it won't be 1. Now we begin our standard code, which I've called a critical section. And except for obtaining the counter, it's exactly the same as what we've seen before. So let's see, how do we get the counter? we bring in 6 bits into the ISR, and remember we changed the shift direction to right, so the bits we're going to get, the end base is 14, so we're going to get 14, 15, 16, 17, 18, and 19. And they're going to come in the high order part of ISR. Here they are. So the high 4 bits of the ISR are the LEDs, followed by the 2 button pin values. We want to get rid of those button pin values, and we want the LED value all the way to the right. So we shift it right. Now the ISR is just the LED value. Now we do what we've done before. We invert, jump, and then update invert of that. I added in some detail for what happens for one particular jump because it was confusing to me. Thought it might be confusing to others. So that ends the code. It's the same as before. When we're done, this instruction releases the latch. In other words, it sets it back to available. That's the end of the first state machine. Second one, very similar. The only difference here is that we're waiting on pin index 1 this time. Remember, the base pin is 14, so we use index 1 to get to pin 15. We debounce the down button. We debounce when it's up. We have a similar wait. Release. All right, so we get the latch. We get the LED values. We update the LED values and put them in the LEDs, and we release the latch. That's it. 29 PIO instructions, 16 in the first one because it had 3 initialization, and 13 in the second. Regular definitions, activate the first state machine, pause for just a sec to allow those 3 initialization lines to run, activate the second. Now just for me, these lines aren't needed. Go to sleep. What we'll do real quick is run it. Hopefully the time will run out. First I will count up on the green button. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and back to 0. Count down. We're at 0, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So we've seen that the buttons in isolation work fine. Now I want to illustrate, because we have 2 state machines competing, I'm going to try to press both buttons at the same time and see what happens. Before I do that, I'm going to get it up to 7. 1, 2, 3, 4, 5, 6, 7. Now I'm going to try to press both buttons at the same time. Watch the high order one as I press this. 1, oh, it blinked. 2, 3, 4. So we saw the high order button flash for just an instant, but the counter is still at 7, as we would expect, since one button press was incrementing, one button press was decrementing. Everything is fine. Now let's make sure that it didn't break anything. Does up still work by itself? 8, 9, 10. Let's check down. 9, 8, 7. Yep, everything works fine. So that's it. I want to, at the bottom though, I added an appendix talking about that flag 4. The flags are kept in the register portion of the PIO 0 specifically. And remember, I gave a reference to the PIO section 3.7 for the list of registers. The IRQ register is a 32-bit register, but only the low 7 bits are used. And notice that the one for IRQ flag 4 is on, which is exactly what you'd expect after the IRQ instruction and before the wait instruction. This was a fun assignment, really challenging. Glad Paul gave it to us. Thanks for watching.